The night sky is a beautiful lie. All that serene darkness is actually filled with a violent, invisible light. This is the cosmic X-ray background, a faint X-ray glow bathing the entire universe. It was discovered by pure accident, and for over 60 years its true nature has been one of astronomy's deepest puzzles. By the end of this exploration, you will understand the 25 key mysteries that make this background glow, a map to the universe's most explosive secrets. We will uncover what this pervasive light reveals about the hidden growth of supermassive black holes, the possible location of the universe's missing atoms, and the ghostly signature of dark matter itself. This journey will show you how a faint, uniform glow can rewrite our story of cosmic evolution. What do you believe is the most profound secret the darkness holds? The first clue came not from a grand telescope but from a tin can shot into the sky. In 1962, a young physicist named Riccardo Giacconi was not looking for a cosmic glow. He was trying to solve a much simpler puzzle to see if the moon, our placid neighbor, was giving off X-rays from the sun's bombardment. His team strapped a simple Geiger counter to the nose cone of a small rocket, launched it for a few precious minutes above the atmosphere, and waited for the data. They expected to see a faint signal from the moon's direction. What they recorded instead was a shock. The instrument did not see a single source. It saw a faint, steady hiss of X-rays coming from everywhere at once, a uniform fog of high-energy light that filled the entire sky. It was as if you stepped outside on a clear, dark night expecting to see stars, and instead found the entire heavens glowing with a soft, invisible light. The initial reaction was pure confusion. This made no sense. Every other form of light, from radio waves to visible starlight, came from distinct points from stars and galaxies. This was a background, a pervasive sea. Giacconi's accidental discovery did more than just add a new color to the cosmic palette. It blew open an entirely new window on the universe, the high-energy X-ray window, revealing a cosmos far more violent and dynamic than anyone had dreamed. And with that open window came the very first and most fundamental mystery. If this light is coming from everywhere, then what, or more terrifyingly, what multitude of things is creating it? This fundamental question created a deep divide among astronomers for decades. Was the cosmic X-ray background a true fog, a smooth, continuous sea of energy with no distinct origin, perhaps from some exotic hot gas spread throughout the cosmos? Or was it an optical illusion, a forest of countless individual points of light, each one a distant, violent event that our primitive instruments simply could not separate? The answer would dictate the entire future of X-ray astronomy. If it was a true fog, it pointed to a universe filled with a mysterious, hot, intergalactic medium, a radical new component of space itself. But if it was a forest, then the background was a census. It was the combined scream of every hidden monster in the cosmos, a collective light from millions of supermassive black holes, exploding stars and colliding galaxies, all too faint and far away to see individually. Resolving this mystery meant building a new kind of eye, a telescope that could see in X-rays. But X-rays are not like visible light. They do not bounce off mirrors, they bury themselves in them. The technological race was on to create instruments with enough sensitivity and sharpness to either see the individual trees in this cosmic forest or confirm the existence of the fog. This was not just an engineering challenge, it was a philosophical one. Were we looking at a new state of the universe or merely a crowd of familiar terrors seen from a great distance? The answer, when it finally came, would reshape our map of cosmic history and lead us directly to the next, even deeper layer of the mystery, the forest one. Decades of observation, culminating with powerful telescopes like Chandra and XMM Newton, finally pierced the haze. They revealed that the vast majority of this cosmic X-ray glow was not a smooth fog, but indeed the combined light of millions upon millions of supermassive black holes feasting on matter in the hearts of distant galaxies. But solving one mystery only deepened another. If we could now see the individual trees, why was there still a faint, uniform light left over? This residual glow, this subtle background hiss that the telescopes could not resolve into points, pointed to something else entirely. It whispered of a second, more elusive component to the cosmic X-ray background, and it connected directly to one of cosmology's most embarrassing problems, the case of the missing atoms. You see, scientists can calculate with remarkable precision from the afterglow of the Big Bang exactly how many ordinary atoms, the protons and neutrons known as baryons, should exist in the universe today. They are the stuff of stars, planets, and us. Yet when astronomers add up all the baryons they can see in galaxies, stars, and cool gas clouds, they come up staggeringly short. Over half of all the normal matter in the universe is simply missing. So where did it go? One compelling theory suggests these missing atoms are not in neat, visible structures, but are instead spread throughout the vast, empty spaces between galaxies. They form a cosmic web of incredibly thin, incredibly hot gas known as the warm-hot intergalactic medium. This WIM is so diffuse, a single cubic meter of it might contain only a single atom, but it is also searingly hot, heated to millions of degrees by the gravitational shocks of the universe's large-scale structure. And gas that hot does something very specific. It glows faintly in X-rays. This is where the two great puzzles collide. That faint, unresolved portion of the cosmic X-ray background could be the collective, whisper-thin signature of the warm-hot intergalactic medium. It could be the glow from the universe's missing atoms finally revealing their hiding place. Proving this, however, is a monumental challenge. It is the astronomical equivalent of trying to hear a single person whispering in a packed, roaring stadium. The roar is the combined light from all those brilliant, point-like black holes. The whisper is the faint, diffuse X-ray emission from the hot gas filaments of the WIM. Our current telescopes are straining at their limits to separate that whisper from the roar. Finding it would not only solve the mystery of the missing baryons, it would confirm that the cosmic X-ray background is a two-part harmony, a chorus of monstrous black holes superimposed over the faint, steaming breath of the cosmos itself. And if that breath is not what we think, if that residual glow holds a different signature, then it points our investigation towards something even more strange and fundamental. But identifying the primary source of the cosmic X-ray background only sharpens the mystery. These are not just any black holes. At the heart of nearly every galaxy, including our own Milky Way, slumbers a supermassive black hole, a gravitational pit weighing millions to billions of times the mass of our Sun. Most are quiet, dormant giants. The ones that create the X-ray glow are the rare few that are awake and feasting. When a torrent of gas, dust, and even stars falls toward such a black hole, it doesn't just vanish. It forms a swirling, superheated maelstrom called an accretion disk, where temperatures soar to millions of degrees. Matter in this disk is shredded by tidal forces and friction, glowing so fiercely it can outshine the entire galaxy that hosts it. This violent engine is an active galactic nucleus, and its intense heat is what floods space with the high-energy X-rays we detect across the cosmos. The sheer power is almost incomprehensible. A single, well-fed active galactic nucleus can emit more energy in 1 second than our Sun will produce in its entire 10 billion-year lifetime. And the cosmic X-ray background tells us that for billions of years across the entire observable universe, millions of these monsters have been screaming in X-rays. Their combined light, stretched and diluted by the expansion of the universe, is what reaches us as that faint, all-sky glow. Yet this explanation creates a new and precise puzzle for astronomers, a cosmic accounting problem of staggering scale. We know active galactic nuclei are the main contributors, but to perfectly match the exact spectrum and intensity of the background we see, we need a very specific census. How many of these active black holes were feasting in the early universe versus more recently? What was the distribution of their sizes and appetites? Were they mostly obscured by thick shrouds of dust or blazing openly? Every model of the cosmic X-ray background is essentially a detailed recipe, and the ingredients are the populations of active galactic nuclei throughout cosmic history. Get the recipe wrong, and the predicted background light doesn't match what we actually observe. The challenge is that our deepest X-ray surveys, while incredible, are still like taking a census of a vast city by only observing the brightest streetlights on the clearest night. We see the most luminous, obvious monsters, but we might be missing a hidden population of fainter, obscured, or more distant active black holes whose combined whisper is essential to the final sum. This accounting is crucial because it is not just about adding up light. It is about writing the biography of supermassive black holes themselves, understanding when and how they grew to such monstrous sizes, and deciphering their role in shaping the galaxies around them. The cosmic X-ray background is the integrated record of their most violent feasts, and we are still learning how to read its fine print. The recipe for the cosmic X-ray background has a secret ingredient we can barely see. For every brilliant, openly feasting black hole we detect, there could be several more hiding in plain sight, shrouded in thick cloaks of cosmic dust and gas. These are the obscured active galactic nuclei, and they are the universe's most powerful ghosts. Their dusty cocoons are so dense they swallow almost all visible light, rendering these monstrous engines nearly invisible to optical telescopes. Yet that same shroud is transparent to the penetrating power of X-rays. While it blocks our view of the visible fireworks, it cannot hide the searing heat of the accretion disk itself. To an X-ray telescope, these hidden monsters shine like brilliant beacons through the fog. This creates a profound observational bias. Our census of the universe's most violent objects is inherently incomplete, skewed toward the ones that are easier to see. We have been counting the roaring giants in the clearing, while an entire population of equally powerful beasts might be lurking silently in the surrounding forest. The cosmic X-ray background strongly hints that this hidden population is vast. To perfectly account for the exact intensity and spectrum of the all-sky glow, models suggest we need a large number of these obscured active galactic nuclei, perhaps even outnumbering the unobscured ones, especially in the early universe. They are the missing voices in the chorus, the ones whose muffled screams contribute a deep, foundational tone to the background we hear. Finding them is a monumental game of cosmic hide and seek. It requires cross-referencing the deepest X-ray surveys with observations in infrared light, which can sense the heat from the obscuring dust itself, and with data from other wavelengths to build a complete portrait. Each confirmed hidden active galactic nucleus is a triumph of detective work, piecing together clues from across the electromagnetic spectrum. Their existence is more than just a statistical necessity. It rewrites the story of how black holes and galaxies co-evolved. If most supermassive black holes spent their formative years shrouded in dust, it means their growth spurts were hidden from view, occurring within thick, natal clouds of material. This changes our timeline and our understanding of the feedback processes that shape galaxies. The hunt for these obscured giants is therefore a hunt for a hidden chapter in cosmic history, a chapter written not in starlight, but in the penetrating whisper of X-rays that slipped through the dust. But the census faces its greatest challenge not with the hidden giants, but with the quiet multitudes. Beyond the brilliant, obscured active galactic nuclei lies a frontier of profound faintness. This is the realm of the low-luminosity active galactic nuclei, the faint end of the luminosity function, and it presents a mystery of sheer numbers. What if the primary contributors to the cosmic X-ray background are not the rare, spectacular monsters, but an uncountable legion of modest, smoldering black holes. Every large galaxy, including our own Milky Way, hosts a supermassive black hole. Most of the time, these black holes are not in a dramatic feeding frenzy. They are in a state of relative quiet, accreting just a trickle of gas, a stellar wind, or the occasional unlucky star. This low-level activity still produces X-rays, but it is a faint whisper compared to the roar of a full-blown active galactic nucleus. The critical question is one of population statistics. For every one brilliantly feasting black hole, how many thousands or millions of these faintly glowing ones exist across cosmic time? Their individual contributions are minuscule, but if there are enough of them, their combined light could be a major or even dominant piece of the cosmic X-ray background puzzle. Our current telescopes, as powerful as they are, hit a fundamental wall when trying to detect these objects at great distances. We can see the faintest nearby active galactic nuclei in galaxies like our own, but spotting their equivalents in the early universe when the background light was being built is currently impossible. They lie below the detection threshold, lost in the noise. This creates a major uncertainty in our cosmic accounting. It is like trying to measure the total light output of a city at night. We can easily count the bright stadium lights and neon signs, the luminous active galactic nuclei, but we have almost no way of tallying the combined glow from every dim porch light, every nightlight in a child's room, every faint dashboard LED in every parked car. If those faint sources are numerous enough, their total light could rival that of the brighter, obvious ones. Astronomers are deeply divided on this point. Some models suggest these low-luminosity active galactic nuclei are the true unsung heroes, providing the essential baseline glow that completes the cosmic X-ray background spectrum. Others argue their contribution is marginal, that the background is truly built by the more luminous, though often obscured, monsters. Resolving this debate requires a leap in sensitivity we do not yet possess. It awaits a future generation of X-ray observatories, telescopes with vastly larger collecting areas and sharper vision, designed to conduct ultra-deep surveys that can finally reach this faint population. Until then, the possibility remains that a hidden ocean of quiet black holes, each sipping rather than gulping, has been shaping the background light all along. Their collective murmur might be the most common sound in the high-energy universe, a testament to the quiet, simmering power that lies at the heart of nearly everything. Yet the roar of supermassive black holes is not the only sound in this cosmic chorus. Scattered like embers throughout the spiral arms of galaxies like our own, another class of monster whispers in X-rays. These are X-ray binaries, and they represent violence on a more intimate stellar scale. An X-ray binary is a dance of death between two stars, or rather, what remains of them. One partner is a normal star like our Sun. The other is a stellar corpse, a neutron star or a stellar mass black hole, the incredibly dense remnant of a massive star's explosive death. Locked in a tight gravitational embrace, the normal star has its outer atmosphere steadily stripped away by its monstrous companion. This stolen gas doesn't fall quietly. As it spirals down toward the neutron star or black hole, it forms a miniature, superheated accretion disk, reaching temperatures so extreme that it shines with a piercing, focused beam of X-rays. These systems are not just theoretical. We observe them within our own Milky Way. Some, like Scorpius X1, are so bright they can outshine 1 million suns in X-rays, serving as nearby laboratories for studying the physics of extreme gravity and matter. This creates a fascinating layer to the mystery of the cosmic X-ray background. We know these stellar-scale powerhouses exist in vast numbers within galaxies. Every spiral and elliptical galaxy likely contains its own population of X-ray binaries, each one a tiny, searing point of high-energy light. So the question becomes a matter of cosmic accounting on a grand scale. How much does this entire population, summed across every galaxy in the observable universe, contribute to the faint all-sky X-ray glow? Are they a minor footnote, their light drowned out by the collective scream of the supermassive black holes at galactic centers? Or could they be a significant, even dominant, source of the background at specific higher energies? The challenge is one of distance and integration. An X-ray binary in a distant galaxy is an incredibly faint point, impossible for current telescopes to pick out individually. But the combined emission from millions of such binaries, each in its own host galaxy, could blend together into a diffuse, uniform haze that our instruments perceive as part of the unresolved background. This is especially true for the highest energy X-rays, where the accretion processes around these stellar remnants are particularly efficient. Unraveling their contribution requires sophisticated modeling, peeling back the layers of the background to see if its spectral fingerprint matches what we would expect from a universe filled with these cannibalistic stellar pairs. Solving this isn't just about balancing a ledger, it teaches us about the life cycle of stars on a cosmic scale, revealing how common these violent binaries are across different types of galaxies and throughout the history of the universe. The faint X-ray glow we see might just hold the integrated history of a billion silent stellar thefts, a background hum of galactic crime written in light no eye can see. But the universe builds structures on a scale that dwarfs even galaxies. Drifting through the cosmic web-like islands in a vast, dark sea are galaxy clusters, the largest gravitationally bound objects in existence. A single cluster can contain thousands of galaxies, all swarming in a common pool of gravity, but the galaxies themselves are merely the visible tip of an immense iceberg. The true bulk of a cluster is an ocean of superheated gas. This intracluster medium is thin, far more diffuse than Earth's atmosphere, but it is also unimaginably hot, heated to tens of millions of degrees by the sheer gravitational violence of the cluster's formation. And gas that hot has a signature, it glows brightly in X-rays. To an X-ray telescope, a galaxy cluster is not a collection of stars, but a colossal, softly glowing cloud of multimillion-degree plasma, often with a brilliant, feeding supermassive black hole at its heart. This presents a new layer to our background mystery. We know these massive, X-ray bright structures exist. We have catalogued thousands of them. So we must ask, does the combined light from every galaxy cluster across the entire observable universe, from the nearby, brilliant ones to the faint, ancient clusters in the distant past, add its own whisper to the cosmic X-ray background? Or have our modern telescopes like Chandra already resolved all of them into distinct, individual sources, leaving no cluster contribution to the unresolved glow? The answer is a delicate puzzle of sensitivity and cosmic evolution. The brightest, most massive clusters nearby are easily seen as individual, extended blobs in X-ray maps. But as we look deeper into space and further back in time, clusters were smaller, less massive, and fainter. There must exist a frontier, a distance where a cluster's X-ray emission becomes so faint and spread out that it blends seamlessly into the background haze, indistinguishable from the sea of distant black holes. Determining where that frontier lies and how much light these faint, distant clusters contribute is not just an accounting exercise. It is a direct probe into the growth of cosmic structure itself. The way clusters assembled over billions of years, how their hot gas pools were heated and enriched with heavy elements from generations of supernova, all leaves an imprint on the specific qualities of the X-rays they emit. If we can measure their collective fingerprint in the background, we can trace the history of how the universe built its largest cities. It offers a census of cosmic construction, a way to weigh the entire population of clusters across time, testing our theories of gravity and dark matter on the grandest scales. The faint, uniform X-ray glow might therefore hold the thermal echo of the universe's architecture rising from the dark. This brings us back to the universe's missing atoms and a glow so faint it has never been directly seen. The cosmic web is not just a theoretical model. It is the large-scale structure of everything, a vast sponge-like network of dark matter and gas, with galaxies and clusters clinging to the densest nodes. Stretching between these nodes are the filaments, immense bridges of thin gas that channel material across the cosmic voids. According to our best calculations, over half of all the ordinary matter, the baryons, should reside in these filaments, not in the stars or galaxies themselves. This is the warm, hot intergalactic medium, the WIM. It is a ghostly plasma, so diffuse that a volume the size of your living room might contain just a single atom. Yet it is also heated by the violent process of cosmic structure formation, stretched and shocked by gravity to temperatures of millions of degrees, and anything that hot should emit a whisper-soft glow in X-rays. This predicted filamentary glow is one of the most sought-after signals in all of astronomy. It is the missing piece of the cosmic inventory, the final hiding place for the atoms we know must exist. The cosmic X-ray background is our best chance to find it. That faint, unresolved portion of the all-sky glow could be, in part, the collective light from a trillion cosmic threads, the thermal signature of the universe's skeleton itself. But detecting it is a challenge of almost impossible subtlety. Imagine trying to see the delicate, glowing strands of a spiderweb that has been draped over the blazing surface of the sun. The brilliant points of active galactic nuclei and galaxy clusters are that sun, overwhelming and dominant. The filamentary glow of the WIM is that spiderweb, a pattern of faint connections lost in the glare. Astronomers are not giving up. They use every trick in the book, searching for the specific, predicted X-ray signature of highly ionized oxygen and other elements in the deepest background spectra. They look for subtle correlations in the X-ray light between known pairs of galaxy clusters, hoping to catch a faint bridge of emission. Every tentative hint, every statistical fluctuation in the data is scrutinized with desperate hope. Finding this glow would do more than just balance the cosmic books. It would provide a direct map of the cosmic web in a form we have never seen, revealing how energy flows and matter is distributed along the grand highways of the universe. It would confirm that the cosmic X-ray background is not just a record of catastrophic events, but also the gentle, thermal breath of the cosmos, the warm hum of its most abundant yet most elusive component. Yet for all its apparent uniformity, the cosmic X-ray background holds a secret pattern. If you could listen very carefully, you would hear that the faint hiss is not a pure, featureless tone. It has subtle lumps and bumps, whispers of structure known as anisotropies. This is the anisotropy puzzle, and it transforms the background from a simple glow into a potential map of the universe's hidden architecture. Imagine you are flying high above a vast, fog-shrouded forest at night. From your vantage point, the forest appears as a uniform, glowing expanse, the collective light from millions of unseen campfires. But if your eyes were sensitive enough, you might notice that the glow is not perfectly even. Some areas are very slightly brighter, others very slightly dimmer. Those tiny fluctuations are not random. They betray the underlying layout of the forest itself, hinting at dense groves of campfires here and sparse clearings there. The cosmic X-ray background is that forest glow, and the anisotropies are our only clue to the arrangement of the campfires within. In this case, the campfires are the millions of active galactic nuclei and the vast reservoirs of hot gas in galaxy clusters and filaments. Their distribution across the sky is not random. They trace the cosmic web, the same vast filamentary structure that governs the placement of galaxies. So, by painstakingly measuring the statistical patterns in the X-ray background's faint light, astronomers are attempting to do something extraordinary. They are trying to sketch the skeleton of the entire observable universe using only X-rays. The challenge is one of incredible subtlety. The fluctuations we are searching for are minuscule, variations in brightness of perhaps 1% or even less against an already faint signal. Detecting them requires not just incredibly sensitive instruments, but mountains of data and sophisticated statistical analysis to separate the true cosmic signal from the noise introduced by our own instruments and the galaxy. It is like trying to discern the pattern on a tapestry by studying the shadow it casts on a wall from a mile away while the light source flickers. Why go through such immense trouble? Because a successful map would be revolutionary. It would show us where the most massive black holes were clustered in the early universe, revealing the environments that nurtured their growth. It could pinpoint the locations of the faint, diffuse hot gas in the cosmic web, providing indirect evidence for the warm-hot intergalactic medium. Essentially, it would give us an X-ray view of the universe's large-scale structure, complementary to the maps we have in visible light or from the cosmic microwave background. Decoding these anisotropies is like learning to read a new language, one where every faint statistical correlation tells a story about gravity, structure, and the violent history of the cosmos. The pattern is there, woven into the fabric of the glow. We are only just beginning to trace its threads. That faint hiss across the sky is not a monotone drone. It has a very specific pitch, a distinct energy signature known as its spectrum. When astronomers break the cosmic X-ray background down into its component colors, so to speak, they find it does not shine equally at all X-ray energies. Instead, it rises to a distinct peak, a cosmic hump centered around an energy of 30 kilo-electron-volts. This is not a random detail. This specific shape is the integrated fingerprint of every single X-ray source in the universe, all blended together and stretched by the expansion of space. The mystery is that reproducing this exact fingerprint with our models is devilishly hard. It is a cosmic jigsaw puzzle where we think we know all the pieces, the brilliant active galactic nuclei, the faint X-ray binaries, the hot gas in clusters, but when we try to fit them together to match the observed hump, they never quite align perfectly. The sum of the parts as we currently understand them does not equal the whole. This tells us something crucial. We are still missing a piece of the puzzle, or we fundamentally misunderstand the pieces we have. Perhaps our census of active galactic nuclei is wrong, and we need more of the heavily obscured kind to soften the spectrum just so. Maybe the contribution from faint X-ray binaries is far greater than we thought, adding a specific high-energy tint. Or perhaps there is an entirely unknown population of sources, something we have not yet conceived of, whose light completes the picture, but the plot thickens further when we consider time. That spectrum we measure today is a single, frozen snapshot, a blend of light that has been arriving from different eras. The glow from a source 10 billion light-years away shows us the X-ray universe as it was 10 billion years ago. The light from a source 5 billion light-years away is a chapter from a more recent cosmic epoch. So the spectrum we see is a palimpsest, a document written over and over again by generations of X-ray sources. To truly understand it, we must ask how it has evolved. How did that characteristic hump sound when the universe was half its current age, or only a quarter? Did the early universe have a sharper, more energetic X-ray tone dominated by voracious young black holes? Or was it a softer murmur shaped by different processes? Unraveling this requires a form of cosmic archaeology, using the deepest X-ray surveys to separate the light from different eras and reconstruct the history of the high-energy sky. It is the ultimate test of our story of cosmic evolution, demanding that we not only account for every source of X-rays, but also understand precisely how their collective song has changed over 13 billion years. The spectrum of the cosmic X-ray background holds one final, sharp note at its highest register. As we push beyond the main hump into the realm of hard X-rays and soft gamma rays, the light does not simply fade away. It persists, creating a stubborn, high-energy tail that stretches up to energies of hundreds of kilo-electron-volts. This is the most penetrating radiation in the entire background, photons so energetic they can punch through material that would stop ordinary X-rays cold. Their very existence points to processes of almost unimaginable violence, the absolute extremes of physics in the cosmos. While the main glow tells the story of superheated gas and accretion disks, this high-energy tail whispers of environments where matter is not just hot, but is being accelerated to nearly the speed of light. The primary suspects are the most extreme members of the active galactic nucleus family, particularly a class known as blazars. A blazar is a supermassive black hole whose powerful jet of accelerated particles is pointed almost directly at Earth. Think of it as staring down the barrel of a cosmic particle accelerator that is light years long. Within those relativistic jets, electrons and other particles are whipped to such fantastic speeds that when they collide with magnetic fields or low-energy photons, they scream out in gamma rays. This process, known as inverse Compton scattering, is a prime factory for the very highest energy photons we detect, but blazars are rare even among active galactic nuclei. Can their collective light really account for the entire high-energy tail we see across the whole sky? Many scientists suspect there must be other contributors, perhaps hidden within the accretion flows of more typical black holes. The very innermost regions just outside the event horizon are cauldrons of such intense gravity and heat that they might naturally produce these hard photons. Or the answer could point to something far more exotic. This unexplored frontier is where conventional astrophysics begins to brush against the edges of fundamental particle physics. Some theorists have proposed that a portion of this persistent high-energy signal could be the long-sought signature of dark matter decay or annihilation. Certain hypothetical dark matter particles, like weakly interacting massive particles, could theoretically decay into pairs of gamma-ray photons with very specific energies. If such a signal were embedded in the cosmic X-ray background, it would be faint, diffuse, and uniform, exactly what we see. This makes the high-energy tail a tantalizing hunting ground, not just for astrophysicists but for particle cosmologists. The challenge is one of clarity and contamination. Our telescopes for this energy range have historically had blurry vision, making it difficult to pinpoint individual sources and separate the true cosmic background from local noise. New missions are being designed to finally bring this spectral frontier into sharp focus, to dissect its light and determine its origin. Is it the combined shriek of a universe filled with misaligned particle beams, or could it contain the first faint glow of the universe's most mysterious substance finally revealing its nature? The high-energy tail is not the only spectral frontier with secrets. At the opposite end of the scale, where X-rays blur into extreme ultraviolet light, lies another persistent anomaly known as the soft excess. This is a puzzling surplus of low-energy X-rays, below about 1 kilo-electron-volt, that seems to permeate the sky. Its presence is a constant reminder that the cosmic X-ray background is not a pure signal from the distant universe. It is a composite, and some of its light comes from right in our own cosmic backyard. Before we can hear the faintest whispers from the edge of time, we must first identify and subtract the local noise. The primary source of this low-energy fog is a vast, tenuous cavity of hot gas surrounding our solar system, known as the local hot bubble. This region, spanning hundreds of light years, is filled with plasma heated to around 1 million degrees, likely by ancient supernova explosions that occurred within the last few million years. We are essentially floating inside a giant, diffuse, X-ray emitting bubble. Its gentle glow forms a veil across the entire sky, a foreground fog that contaminates our view of the true cosmological background. But the local hot bubble is not the only local culprit. An even more subtle process adds its own whisper to the mix solar-wind charge exchange. As the stream of charged particles from our own sun, the solar wind, races outward, it occasionally collides with neutral atoms drifting in the interstellar medium around our solar system. During these collisions, an electron can jump from the neutral atom to a highly charged ion in the solar wind. When that electron settles into its new home, it releases a tiny pulse of energy, often as a soft X-ray. This process happens constantly in the space around us, creating an ever-changing, faint X-ray halo that depends on the sun's activity and our position in its magnetic field. Disentangling this local foreground from the true cosmic signal is one of the most complex and critical puzzles in X-ray astronomy. It is the ultimate exercise in cosmic subtraction. Astronomers must build intricate models of the local hot bubble's shape and temperature, and monitor the fluctuating X-ray fog from solar wind charge exchange to peel them away from the all-sky data. Any error in this delicate process directly impacts the accuracy of our measurements of the faint, unresolved cosmic background. If we over-subtract, we might erase the true signal from the distant warm-hot intergalactic medium. If we under-subtract, we could mistake a local ripple for a profound cosmological discovery. This foreground fog forces a profound humility upon the search. It reminds us that to see the universe clearly, we must first understand the intricate glowing room in which we stand. But the cosmic X-ray background may hide a clue to the greatest mystery of all. Woven into that faint, uniform glow could be the first direct signal from dark matter itself. This is not a metaphor. For decades, scientists have known that most of the matter in the universe is invisible, a ghostly substance that reveals itself only through its gravitational pull on galaxies and stars. We call it dark matter, but its fundamental nature remains utterly unknown. The cosmic X-ray background offers a unique hunting ground. If certain theoretical dark matter particles exist, they might not be completely stable. They could occasionally decay or collide and annihilate one another, and if they did, that process would release energy, often in the form of photons at very specific wavelengths. For a popular candidate known as the sterile neutrino, a hypothetical heavier cousin to the ordinary neutrino, that decay signature would be a faint, sharp spike of X-ray light at a precise energy, a spectral line etched into the smooth continuum of the background. Imagine listening to the static hiss of an old radio, and amidst the noise you detect a single, pure, unwavering musical note. That note would be the sterile neutrino's calling card. The cosmic X-ray background is that static hiss, and astronomers are using incredibly sensitive spectrometers to listen for that one perfect note. They are not searching for a bright point source, but for a subtle excess, a faint bump in the data that appears uniformly across the entire sky, exactly as you would expect from a component of matter that permeates the whole cosmos. The hunt is incredibly difficult. It requires separating this hypothetical signal from the astrophysical foregrounds, from the emission lines of hot gas in our own galaxy, and from the instrumental noise of the telescopes themselves. It is a search for a whisper within a whisper, yet the potential reward is beyond measure. Finding such a line would be a monumental, Nobel Prize-worthy discovery. It would not only identify what dark matter is made of, but it would also provide a new tool to map its distribution throughout the universe, using its own faint X-ray glow as a guide. Every non-detection, every time the data shows no spike at a predicted energy, helps rule out a candidate and narrows the search. So far, no definitive signal has been found, but a few tantalizing, unconfirmed anomalies have sparked intense debate. The search continues with ever more precise instruments, because the possibility remains that the answer to the dark matter puzzle has been bathing us in a faint, high-energy light for the entire history of the universe, waiting within the glow for us to learn how to see it. The hunt for dark matter's signature is not the only spectral detective story written in the X-ray background. Beyond the search for one perfect note, astronomers have found themselves confronted by a series of fleeting, unidentified lines. These are mysterious bumps and dips in the background spectrum at specific energies that do not correspond to any known atomic transition or process we understand. They are like finding pages written in an unknown language within a familiar book. One of the most famous and persistent of these mysteries emerged from data collected by the XMM Newton Space Telescope over a decade ago. At an energy of around 3.5 kilo-electron-volts, a faint but statistically significant emission line seemed to appear in the combined X-ray glow from galaxy clusters and the background itself. The immediate problem was that no known atom, no element on the periodic table, emits a line at that precise energy under normal cosmic conditions. The scientific community erupted with possibilities. Could it be the decay of a sterile neutrino, that promising dark matter candidate? Or was it pointing to something entirely different, like the existence of a new, exotic form of matter or a previously unknown atomic process occurring in the hot plasma of galaxy clusters? For years, this 3.5 kilo-electron-volt line was a tantalizing specter, a hint of new physics just beyond our grasp. But in science, extraordinary claims require extraordinary evidence, and follow-up observations with other telescopes like Chandra and Hitomi failed to confirm the signal with the same strength or clarity. The line began to fade from the data, likely a complex artifact of instrumental effects or the challenging subtraction of foreground X-ray emission from our own galaxy. Yet its ghost lingers, a powerful lesson in caution and the immense difficulty of this work. It demonstrated how the cosmic X-ray background serves as a cosmic laboratory for particle physics, a place where the conditions are so extreme they might reveal processes impossible to recreate on Earth. The failure to confirm one line does not end the search, it refines it. Astronomers now scrutinize every subtle feature in the background spectrum with even greater rigor, knowing that the next unidentified line could be a statistical fluctuation, an instrumental quirk, or a genuine window into physics beyond the standard model. It might signal the presence of exotic particles, unknown states of quark matter, or even the subtle effects of extra dimensions. Each unexplained feature is a question mark etched into the light of the cosmos, a silent challenge to our understanding of the fundamental rules that govern reality. The universe writes its most violent stories in transient light. Amidst the steady glow of feeding black holes, there are sudden, brilliant screams that flare and fade within months or years. These are tidal disruption events, and they are among the most cataclysmic single acts a supermassive black hole can perform. Imagine a star, much like our own Sun, on a routine orbit through its galaxy. Through a chance gravitational interaction, its path is altered, sending it on a fatal dive toward the galactic center. As it approaches the black hole, the star does not simply fall in. The difference in gravitational pull between the side of the star nearest the monster and the side farthest away becomes overwhelming. This tidal force stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin stream of gas in a process called spaghettification. The stellar debris does not vanish. About half of it is flung away into the darkness, while the other half forms a temporary, incredibly hot accretion disk around the black hole. As this disk forms and the gas spirals inward, it heats to millions of degrees, unleashing a tremendous flash of X-rays and ultraviolet light that can briefly outshine the entire host galaxy. For a few glorious months, this tidal disruption event becomes a beacon, a temporary active galactic nucleus fueled by the destruction of a single star. With modern sky surveys scanning the heavens constantly, we are now catching more and more of these spectacular stellar deaths. Each one is a unique laboratory, teaching us about black hole masses, stellar physics, and the dynamics of galactic centers. But they present a new wrinkle in our accounting of the cosmic X-ray background. The background is a time-averaged glow, the integrated light over billions of years. Tidal disruption events are not steady contributors. They are flashes in the pan, brilliant but brief, so the mystery is one of statistics and history. If we add up the total X-ray energy released by every tidal disruption event that has ever occurred in the observable universe and spread that energy evenly across cosmic time, does it amount to a significant flicker in the background? Or is it merely a rounding error drowned out by the constant roar of the persistently feeding black holes? The answer depends on how common these events truly are. Current estimates suggest that in a galaxy like our Milky Way, a star is torn apart by the central black hole only about once every 10,000 to 100,000 years. But with hundreds of billions of galaxies in the universe, that still means a staggering number of these explosions are happening across the cosmos at any given moment. Their collective time-averaged light could be a non-negligible, intermittent component of the background, like the combined brief flashes from a universe full of camera strobes. Pinpointing their exact contribution is incredibly difficult. It requires not only finding more of these events to better understand their true rate and energy output, but also modeling how that rate might have changed over cosmic history. Were tidal disruption events more common in the younger, more densely packed universe? Each new discovery adds a data point, helping us understand whether the faint X-ray glow we see includes, woven into its fabric, the silent echoes of a trillion stellar deaths. Buried within that ancient light are the very first monsters. The cosmic X-ray background is not just a record of black holes, it is a fossilized timeline of their birth. To understand the most brilliant quasars we see shining when the universe was less than 1 billion years old, we must confront an impossible problem. How did supermassive black holes weighing billions of suns assemble so quickly after the Big Bang? They had no time to grow slowly. The faintest, most distant X-ray photons in the background may hold the answer, carrying whispers from the elusive seeds from which these giants sprang. These seeds are the missing link in cosmic evolution. Were they the remnants of the universe's very first gigantic stars, collapsing directly into black holes weighing hundreds of suns? Or did they form from the direct collapse of massive primordial gas clouds, skipping the star stage entirely to create black hole seeds thousands of times more massive from the very beginning? Each theory leaves a different imprint on the early X-ray sky. The direct collapse seeds would have been brighter, more powerful X-ray sources from the start. The stellar remnant seeds would have been fainter, more numerous, and taken longer to grow. The integrated light from this first generation, stretched and diluted by 13 billion years of cosmic expansion, is now woven inextricably into the faint tapestry of the background. Finding it is the ultimate archaeological dig. We must look for active galactic nuclei at such immense distances that their light is redshifted far beyond what our telescopes typically see. Their X-ray signatures are shifted down into softer energies, and they are incredibly faint, often just a handful of photons collected over weeks of observation. These are not the brilliant, obvious quasars. They are the quiet, early feeders, the adolescent black holes caught in the act of their first major growth spurts. Every deep X-ray survey is a search for these ghostly infants. When we find a candidate, it is a monumental discovery, a single data point that helps constrain the entire story of how structure emerged from the primordial dark. The cosmic X-ray background is the sum of all their nursery songs. By carefully measuring its properties and comparing it to the deepest pencil beam surveys that probe specific patches of sky, astronomers are slowly reverse engineering the population of the first black holes. How many were there? How bright were they? How quickly did they switch on? The background glow is the integrated answer, a composite photograph of the universe's first dark hearts beginning to beat. The titanic energies released by these black holes do not simply vanish into the void. They are a cosmic regulatory force, a feedback mechanism that sculpts the destiny of galaxies. When a supermassive black hole enters its active phase, the radiation and powerful jets it emits can blast through the surrounding galaxy with the force of 1 billion supernovae. This energy can heat vast reservoirs of cold gas, the very fuel for new stars, preventing it from collapsing. It can even drive galactic winds that eject material entirely, starving the galaxy of its future building blocks. This process, known as active galactic nucleus feedback, is thought to be the reason why massive galaxies are not even larger, and why the era of frenzied star formation in the universe has largely ended. The energy for this cosmic regulation has to go somewhere. After stirring the galaxy, it ultimately dissipates into the vast spaces between galaxies, the intergalactic medium, potentially helping to heat it to the millions of degrees required for it to glow in X-rays. This creates a profound and direct link between the cosmic X-ray background and the story of galaxy evolution. The background is essentially a fossilized record of that feedback energy, a measure of the total heat dumped into the cosmos by screaming black holes over 13 billion years. So we can ask a critical question: does the energy budget add up? If we take the total X-ray light in the cosmic background and work backwards, calculating the total power that must have been released by all the active galactic nuclei in history, do we get a number that matches what our models of galaxy evolution require? Is there enough energy in the background to explain how galaxies were quenched and shaped? Intriguingly, there are hints of a discrepancy. Some calculations suggest the energy recorded in the cosmic X-ray background might be too low. It may not fully account for the powerful feedback needed to explain the galaxy population we see today. This is the mystery of the missing feedback energy. It forces us to reconsider our accounting. Perhaps a significant portion of the black hole's energy output is in forms that do not efficiently heat gas, like powerful jets that punch out into the voids without depositing their energy locally. Or maybe our census of black holes is still incomplete, missing a population whose energy contribution is vital. Resolving this budget is like auditing the universe's power company, ensuring that the energy spent matches the work done in shaping the cosmos. If the numbers do not align, it means a fundamental chapter in the story of how galaxies live and die is still waiting to be written. Even our most powerful eyes in the sky do not always agree. This is the cross-calibration conundrum, a fundamental technical puzzle that sits beneath every grand cosmic theory. The telescopes we rely on to measure the faint X-ray glow, Chandra, XMM Newton, New Star, and Erecita, are masterpieces of engineering, each designed with unique strength. Chandra boasts exquisite angular resolution, seeing fine details like a cosmic hawk. XMM Newton has a huge collecting area, gathering photons like a wide net. New Star specializes in the highest energy hard X-rays, and Erecita performs all sky surveys with remarkable sensitivity. Yet when they point at the same patch of seemingly empty sky to measure the cosmic X-ray background, they can return subtly different answers for its exact brightness and the shape of its spectrum. It is as if four of the world's finest thermometers placed in the same room gave four slightly different readings. The discrepancies are not large, often within a few percent, but in the realm of precision cosmology, where we are hunting for 1% fluctuations or faint spectral lines from dark matter, a few percent is the difference between a profound discovery and a dead end. This calibration uncertainty casts a shadow over everything. It means that before we can confidently say what the background is telling us about missing atoms or black hole growth, we must first be absolutely certain we are measuring it correctly. The root of the problem lies in the extreme difficulty of calibrating an X-ray telescope on the ground. Unlike optical telescopes that can be tested against standard light sources, X-ray instruments require specialized particle accelerator-based calibration facilities that can never perfectly replicate the conditions of space. Each telescope has its own complex array of mirrors, detectors, and filters, each with tiny, inherent quirks in how they absorb, reflect, or count incoming photons. A minute difference in the assumed efficiency of a detector at a specific energy, or a subtle modeling of how the telescope's optics scatter stray light, can propagate through the data processing and change the final result. Resolving these differences is a painstaking, collaborative international effort. Astronomers use celestial calibration sources, like the steady X-ray emission from isolated neutron stars or the predictable afterglow of supernova remnants, as cosmic standard candles. They meticulously compare data from different observatories, building intricate software models to harmonize their measurements. This work is unglamorous but utterly essential. It is the process of building a common language so that Chandra, XMM Newton, New Star, and Erecita can all tell the same story. Until they do, the true properties of the cosmic X-ray background remain slightly blurred, and every mystery it holds waits just out of perfect focus for the moment our instruments finally sing in perfect unison. Even our most precise measurements are haunted by a fundamental uncertainty. This is the challenge of cosmic variance, and it strikes at the very heart of how we interpret the faint X-ray glow. We must remember that the cosmic X-ray background is not a smooth, fundamental field like the cosmic microwave background. It is a statistical construct built from the combined light of countless discrete, clustered objects, active galactic nuclei, galaxy clusters, and filaments. Unlike any census taken from a sample, the result depends on where you point your telescope. Imagine you are tasked with estimating the average population density of a vast, dark forest. You are given a single, powerful flashlight. You shine it into one small, random patch of woods and count the trees you see. That count gives you an estimate. But what if, by pure chance, you happen to shine your light on a particularly dense grove? Your estimate would be too high. Conversely, if you lit up a sparse clearing, your count would be too low. Your single sample is not perfectly representative of the entire forest. This is cosmic variance in a nutshell. For the cosmic X-ray background, the flashlight is our most powerful X-ray telescope, like Chandra, and the small patch of woods is a deep field observation, a long, dedicated stare at a seemingly blank piece of sky to probe the faintest sources. These deep fields are our windows to the distant universe, but they are just that, windows, not the entire view. The number of faint active galactic nuclei or the apparent strength of the unresolved glow in that one specific window can fluctuate simply because of the underlying, lumpy distribution of matter in that particular line of sight. We might be looking down a relatively empty corridor or straight into a dense knot of the cosmic web. Quantifying this sampling uncertainty is not just academic, it is vital for claiming any discovery. Suppose a deep field measurement finds a slight excess of soft X-rays, a hint that could be the warm-hot intergalactic medium. Before we can celebrate, we must ask, is this a real universal signal, or did we just get lucky and point at a patch of sky that happens to have a bit more hot gas along our line of sight? The only way to beat cosmic variance is with more data, more independent deep fields scattered across the sky, building up a statistical sample that averages out the lumps. It is a slow, painstaking process, a reminder that to see the true face of the cosmos, we cannot trust a single glance, no matter how long and deep it may be. A supernova is the universe's ultimate foundry, forging heavy elements in a blast of unimaginable power. When a massive star reaches the end of its life and explodes, it does not simply vanish. The expanding shockwave, traveling at thousands of kilometers per second, slams into the surrounding interstellar gas, heating it to millions of degrees. This creates a brilliant, expanding bubble of hot plasma that can shine intensely in X-rays for thousands of years. Within a single galaxy undergoing a burst of star formation, hundreds or thousands of these supernova remnants can be glowing at once, each one a temporary but powerful X-ray beacon. And that is just one piece of the puzzle. As we discussed earlier, these stellar nurseries also produce X-ray binaries, those cannibalistic pairs of a normal star and a stellar corpse. In a galaxy busy making stars, you make a lot of massive stars, and massive stars die quickly, leaving behind neutron stars and black holes. This means a star-forming galaxy is also a factory for X-ray binaries. So we have a clear picture. A galaxy like our own Milky Way in its quieter periods produces a soft X-ray glow from a population of older binaries and remnants. But a galaxy in a frenzy of creation, a starburst galaxy, should be absolutely blazing with high-energy light from its countless supernova shocks and young, hungry binaries. This presents a critical and often overlooked mystery in our accounting of the cosmic X-ray background. We have been understandably focused on the brilliant central monsters, the active galactic nuclei. But what about the collective hum from all the normal galaxies, the ones without a brilliantly feeding supermassive black hole? Across the entire universe, for every one galaxy with an active nucleus, there are thousands upon thousands of ordinary galaxies, many of them forming stars at a steady or even furious pace. If you add up the X-ray light from every supernova remnant and every X-ray binary in every spiral and irregular galaxy across cosmic time, what do you get? Does that sum create a significant portion of the faint, unresolved glow we measure? Or is it merely background noise, completely washed out by the far more powerful signal from active galactic nuclei? This is not a settled debate. Some models suggest that at the very lowest X-ray energies, the combined emission from these star-forming galaxies could be a major, even dominant, component of the cosmic X-ray background. Their light is typically softer, less penetrating than the harder X-rays from the accretion disks of black holes. It could provide the gentle, diffuse underpinning to the more energetic hump. Other analyzers argue that while their total contribution is measurable, it is ultimately subdominant, a subtle flavor in a stew dominated by the taste of black holes. The challenge in resolving this is a familiar one: detection limits. Our telescopes can easily see the X-ray emission from nearby star-forming galaxies. We can study individual supernova remnants like Cassiopeia in our own galaxy, and we can measure the total X-ray output of a starburst galaxy like Messier 82. But doing this for galaxies at vast distances, when the universe was young and star formation was at its peak, is incredibly difficult. Their faint, extended X-ray glow blends into the sea of other faint sources. To assess their true cosmic contribution, astronomers must use statistical stacking techniques, combining the X-ray signal from thousands of faint, distant galaxies detected in optical and infrared surveys to tease out their average X-ray brightness. Each new deep survey provides more data for this cosmic census, slowly refining the number. The answer matters profoundly because it connects the high-energy sky directly to the story of star formation itself. If star-forming galaxies are a major part of the background, then the cosmic X-ray glow becomes not just a record of black hole growth, but also a fossilized map of the universe's stellar baby boom, a shimmering afterglow from the era when the cosmos forged most of its stars. These ghostly stars may be writing their own faint chapter in the X-ray story. Galaxy clusters are not just galaxies and hot gas, they are also filled with a sea of lost suns. Over billions of years, as galaxies swing past each other in the cluster's dense core, their gravitational tides pull and stretch them, stripping away countless stars. These orphan stars do not belong to any galaxy anymore. They drift freely in the immense spaces between the galaxies, forming a faint, omnipresent haze known as intracluster light. To the eye, it is a whisper-thin, ghostly glow barely detectable against the black of space. But within that vast population of wandering stars, a certain percentage will not be alone. They will exist in binary pairs, and some of those pairs will contain the stellar corpses we have met before, neutron stars or black holes. These are intracluster X-ray binaries, and they present a fascinating possibility. Could this diffuse ocean of stars, each one a potential host for a faint X-ray source, produce its own collective, truly diffuse X-ray glow that adds to the cosmic X-ray background on the scale of entire clusters. The idea is compelling because it connects two great puzzles: the origin of the faint background and the fate of stars in the most violent neighborhoods of the universe. We know intracluster light exists, and we know the physics that creates X-ray binaries. It seems almost inevitable that some of those wandering stars are quietly feeding matter to a compact companion, glowing faintly in X-rays as they do so. The challenge, as always, is one of detection and separation. The individual glow from one such intracluster binary would be incredibly faint, lost in the glare of the cluster's central supermassive black hole and its multimillion-degree gas. Their signal would not be a point, but a subtle, extended haze that follows the distribution of the intracluster starlight itself. To find it, astronomers must perform a kind of cosmic subtraction. They take deep X-ray images of galaxy clusters and meticulously remove the emission from all the known point sources, like active galactic nuclei in the member galaxies, and then model and subtract the smooth, hot glow from the intracluster gas itself. What remains in the data, if anything, could be this hypothesized population of stellar ghosts. Some tantalizing studies have reported an excess of soft X-ray emission in the cores of a few clusters that cannot be explained by the hot gas alone, and its distribution seems to loosely match the intracluster starlight. Could this be the signature we are looking for? If confirmed, it would mean that the cosmic X-ray background, especially around clusters, includes not just the roar of gas and the scream of black holes, but also the combined whisper-soft sigh of a trillion exiled stars, each one potentially hosting a silent, stellar-scale drama. It transforms the background from a mere energy record into a narrative of stellar displacement and survival, a high-energy testament to the stars that were lost when galaxies collided. The glow we measure today is a single frame from a 13 billion-year-long film. But is that frame truly frozen? The cosmic X-ray background appears constant on human timescales, a permanent feature of the high-energy sky. Yet this constancy is an illusion of our brief perspective. The primary sources of this light, the active galactic nuclei, are not eternal engines, they have duty cycles. A supermassive black hole may feast violently for a few million years, blazing as a brilliant quasar, before its fuel supply dwindles and it falls into a quiet slumber that could last 100 times longer. Across the cosmos, millions of these monsters are constantly switching on and off in an unsynchronized, grand cosmic rhythm. This means the background light itself must be flickering very slowly on timescales of millions of years. The integrated glow we see is the average of this endless turning on and turning off. But could we ever detect that flicker? Could we see the cosmic X-ray background change? The idea seems preposterous. Our observational history spans mere decades, a blink compared to the million-year cycles of these giants. We are trying to measure the pulse of a continent by watching a single grain of sand for 1 second. Yet there might be a way. If we could compare the X-ray background we measure today with a snapshot from the distant past, we could look for a difference. And we have such a snapshot, but it is not a direct one. The light from the most distant quasars has been traveling to us for over 10 billion years. Along its journey, some of that light passes through the vast filaments of the warm, hot intergalactic medium. The hot gas in those filaments can absorb specific X-ray wavelengths, creating tiny, characteristic dips in the quasar spectrum. The strength of those absorption dips depends on the intensity of the background X-ray light that is illuminating and heating the gas at that specific time and place in cosmic history. By studying these fossilized absorption lines in the light of quasars at different distances, astronomers can, in principle, reconstruct how the intensity of the cosmic X-ray background has changed over billions of years. It is an incredibly subtle and difficult measurement, like trying to determine the brightness of a flashbulb by studying the shadow it cast on a wall a decade ago. Early attempts suggest the background was indeed stronger in the past, peaking around the time when black hole activity was at its most frenzied and has since gently faded. But confirming this variability with precision would be a monumental discovery. It would allow us to read the duty cycle of supermassive black holes directly from the sky, to understand not just how many existed but how often they were awake. It would transform the background from a static picture into a dynamic movie, revealing the long, slow heartbeat of the high-energy universe. The faint glow we measure is only as clear as our instruments allow. Our current telescopes, for all their power, are straining at their limits, their vision blurred by the very challenges we have just explored. But the next generation of eyes is already on the drawing board, and they promise to bring the cosmic X-ray background into a focus we have never before achieved. Leading this charge is the X-ray Imaging and Spectroscopy Mission, or XRISM, a joint venture by JAXA and NASA that launched just last year. Its primary weapon is a revolutionary microcalorimeter, an instrument so sensitive it can measure the energy of individual X-ray photons with a precision over 100 times better than any previous observatory. This is not just an incremental improvement, it is a leap into a new realm of clarity. For the cosmic X-ray background, XRISM acts like a master linguist for the spectral whispers we have been struggling to hear. Its exquisite resolution will finally allow astronomers to separate the overlapping emission lines from hot gas in our own galaxy from the true cosmological signal. It will hunt for the specific, predicted spectral signatures of the warm-hot intergalactic medium with unprecedented rigor, searching for the telltale lines of highly ionized oxygen in the faint background haze. And perhaps most thrillingly, it will conduct the most sensitive search yet for a dark matter decay line, listening for that single, pure note from a sterile neutrino with a clarity that could finally confirm or rule out this leading candidate. XRISM is the precision scalpel designed to dissect the spectrum of the glow and identify its faintest, most elusive components. But to truly understand the forest, we must see every single tree. That requires a telescope of staggering power, one that can conduct ultra-deep surveys with both immense light-gathering area and sharp vision. This is the mission of Athena, the Advanced Telescope for High-Energy Astrophysics, a European Space Agency flagship project slated for the 2030s. Athena's design is breathtaking. Its X-ray mirror will have a collecting area over 100 times larger than XMM newtons, and its instruments will combine high-resolution spectroscopy with wide-field imaging. For the cosmic X-ray background, Athena will be a game-changer. It will resolve over 90% of the background into individual point sources, finally lifting the veil on the faintest active galactic nuclei and X-ray binaries that have eluded us. It will conduct a definitive census, determining once and for all the true population of obscured black holes and low-luminosity active galactic nuclei, solving the accounting mystery of the background's origin. Furthermore, by mapping the hot gas in millions of galaxy clusters and groups, Athena will precisely measure their integrated contribution to the glow and trace the growth of cosmic structure through X-rays. It is the ultimate surveyor, built to complete the source catalog that the background implies must exist. Looking even further ahead to the 2040s lies a concept that could peer into the cosmic dawn itself. NASA envisioned Lynx X-ray Observatory represents the next logical, monumental step. With resolution even sharper than Chandra's and sensitivity far greater, Lynx would be designed to see the unseeable. Its primary goal regarding the background is to find the first black holes. Lynx would detect the faint X-ray glow from the accretion disks around the direct collapse seeds and early stellar remnant black holes in the infant universe, directly probing the era of cosmic dawn. It would see the X-ray emission from the very first low-mass galaxies, quantifying the contribution from early star formation and supernova to the primordial background. Lynx would also map the warm-hot intergalactic medium in emission, not just in absorption, tracing the faint filaments of the cosmic web directly and weighing the missing baryons at last. It is the microscope for the early universe, capable of watching the first sparks of high-energy light switch on and begin to weave the background we see today. These observatories are not just machines, they are promises. They represent our collective determination to read the story written in that faint all-sky hiss. XRISM will define the chemical and particle language of the glow. Athena will count its authors with definitive authority. Lynx will travel back to watch them write their first words. Together, they form a decades-long campaign to solve the 25 mysteries of the cosmic X-ray background, transforming it from a profound puzzle into a refined tool. This high-energy glow will cease to be a mystery to solve and become a standard ruler to measure by, a detailed history book of black hole growth, galaxy evolution, and large-scale structure. The faint light that first confused us will ultimately illuminate the darkest chapters of cosmic history. This final frontier is not in the sky but in our own understanding. We have journeyed through 24 profound mysteries of the cosmic X-ray background, from its accidental discovery to its potential as a dark matter detector. But the 25th and perhaps most enduring mystery is philosophical. What does solving it actually mean? Will we ever reach a point where we can declare the cosmic X-ray background fully resolved, with every last photon accounted for and its origin story complete? Or is this a chase with no finish line, a quest where each new generation of telescopes simply reveals a fainter, more elusive population of sources we never knew existed? This is not just a technical question, it is a question about the nature of discovery itself. Consider the cosmic microwave background, the afterglow of the Big Bang. For decades, it was a single profound mystery, a uniform glow that confirmed our universe had a hot, dense beginning. Today, that same glow is no longer a puzzle to be solved, it is a precision tool. Astronomers measure tiny fluctuations in its temperature to map the infant universe's structure, to weigh neutrinos, and to constrain the nature of dark energy. It transitioned from a question into an answer. The cosmic X-ray background is on the same trajectory, but its path is far more complex. Its light is not from a single primordial event, but from the sum of every violent, high-energy process across all of time. Its completion will not be a single eureka, a moment, but a gradual convergence. We will know we are approaching completion when the predictions of our models, informed by observatories like Athena and Lynx, match the observed background glow with such precision that any discrepancy points not to a missing source but to new physics. The unresolved fraction will shrink from a dominant unknown to a minor anomaly, and then perhaps to a measurable signal of something truly exotic. Yet there is a beautiful paradox in this pursuit. The very act of resolving the background into individual sources requires unimaginable sensitivity, and that sensitivity will inevitably unveil new classes of faint objects we cannot currently dream of. It is like using a better microscope to study a drop of pond water, only to discover an entirely new ecosystem of microscopic life. We may solve the mystery of today's background, only to find it has been hiding a deeper, subtler one beneath. So perhaps the ultimate answer is that the cosmic X-ray background will never be fully solved in a static sense. Instead, it will evolve. It will transform from a confusing fog into a detailed historical record, and from that record into a refined instrument for measuring the cosmos. Its faint light will cease to ask us what am I, and will instead help us answer the greater questions of where we came from and what the universe is made of. The journey to understand it is not a path to an end, but the opening of a permanent new window on reality. That faint glow is a living archive of cosmic violence. It is not static noise, but a dynamic, layered record of the universe's most energetic history. we have journeyed through 25 profound mysteries, from its accidental discovery in a tin can rocket to its potential as a map for dark matter. Each puzzle interlinks, revealing that this background light is far more than a simple hiss. It is the integrated story of supermassive black holes growing in hidden nurseries, of galaxies being shaped by their own monstrous hearts, and of the universe's missing atoms hiding in million-degree filaments. It is a fossilized timeline of stellar cannibalism, galactic collisions, and the first sparks of high-energy light after the Big Bang. Solving these interconnected mysteries is not an academic exercise. It is the key to writing a complete biography of our cosmos, understanding how the invisible architecture of dark matter guides the placement of everything we see, and how the violent feedback from black holes ultimately made galaxies like our own possible. The cosmic X-ray background proves that the darkness is not empty. It is filled with whispers, with observatories like XRISM, Athena, and links on the horizon. We are building the ears to finally hear them clearly. The next monumental discovery in the invisible sky could come at any moment, rewriting our story once again. So stay curious, look up at the serene night and remember the hidden violence, the faint glow, and the countless secrets still woven into that darkness. Which of these 25 mysteries fascinates you the most? Let us know in the comments below.